So today is we're going to talk about action potential propagation. And last time we'd gotten to the point where we had clustered a group of voltage-gated channels at one region, one distinct and circumscribed region on a membrane, and then said the remainder of that membrane contained only leak channels. And then I asked you to think about what you thought would happen to the action potential if it was generated at the one restricted spot and how it would then change over the distance of that membrane. We'll pick that up at first today. Then what we'll do is we'll move on, once we've talked about propagating potentials in membranes that lack voltage-gated channels. Then we're going to talk about propagating potentials or an action potential in unmyelinated axons. Now these are going to be neurons that have their axons or conductal regions that are not wrapped in myelin, so they're unmyelinated. And we'll see in these neurons, all of the voltage-gated channels are lined up side by side. There's no separation among them. And we'll see then that the opening of one channel leads to the opening of the next, much like dominoes being dropped and then forcing the dropping of the adjacent dominoes. It turns out about the fastest we can propagate a potential in these sorts of axons in mammals is at about 1 meter per second. To gain the kinds of speeds we typically think about of action potential propagation, the movement of these electrical signals, the trick is to myelinate axons. And we talked about myelination. We emphasized the ideas of how Schwann cells in the periphery and oligodendrocytes in the central nervous system generated those concentric rings of myelin by laying down layer after layer of cytoplasm bounded by the plasma membranes. We then emphasized that there were regions in those axons or conductal regions that remained unwrapped, and those were the nodes of Ranvier. What we're going to find here today is when we talk about myelinated axons is that those nodes of Ranvier are sites where the voltage-gated channels, identical to the ones we see in the unmyelinated axons, identical to the ones that we clustered in one region in our thought experiment, that these voltage-gated channels are now found only at the nodes of Ranvier. This brings up a couple of important ideas. First, it is the myelination and the clustering in the voltage-gated channels of the nodes of Ranvier which increases conduction velocities upwards of 110 meters per second. But to really recognize the mechanism of how myelination increases the conduction velocities to such a great degree, we have to spend a little bit of time down in the weeds talking about some electrical events. The first electrical event I want to start talking about and thinking about is the concept of capacitance. Now, if you've had some electronics in your background, you'll immediately recognize this term. But what I want to demonstrate here with the concept of capacitance is to bring it back not from the electrical engineering concept, but bring it back to biology. And in biology, the capacitor is the phospholipid bilayer. The engineers among you will recognize the phospholipid bilayer as the dielectric. And what we'll do then is we're going to separate positive and negative charges across the phospholipid bilayer. Now remember, the phospholipid bilayer is vanishingly small. It's only about 6 to 7 nanometers in width. But yet, because of the phospholipid tails, because of the fatty acid side chains, it is not a very good conductor. So we have a non-conducting medium that's exquisitely thin, and we can separate charge across that non-conducting medium. That's called a capacitor. What we'll see then is the membrane, the physiological membrane, the phospholipid bilayer, is a really great capacitor. And that has implications for both the unmyelinated and the myelinated axons. We're going to see that one of the major effects of the myelin is to reduce the capacitance. And we're going to see that one of the complications of the capacitance is that because of all this charge stored along the inner membrane of the cell, because of all of this tremendous amount of charge, that charge has to be dissipated before we can get appreciable amounts of ions moving through the channels. So we're going to talk about a two-step activity, where before we simply opened the channels and ions moved through, and we got movement of ions through a channel. Here we'll see that it's a two-step arrangement. We have to first offset or discharge the capacitance along the membrane. And much of the charge coming through the channels will in fact do that. And then most of that capacitance needs to be discharged before we can begin moving current, moving ions through the channels. And we'll see how this limits the rate of propagation in unmyelinated axons. But we'll also see that by myelinating the axon, by separating the inside of the axon and the outside world by layer upon layer of a non-conducting medium, we now separate the charge so much that there's very little capacitance along the internodal regions. And because there's so little capacitance along the internodal regions, we'll see then that ions coming into the node can now have their electromagnetic effect. Now, they're not going to take a walk. They're not going to walk the millimeter or millimeter and a half from one node to the next. But each of those ions will have an electromagnetic field. And thousands of ions coming into the axon will generate a local electromagnetic field. But remember, the inside of the axon is a salt solution. So almost instantaneously, that electromagnetic field propagates from one node to the next. And that electromagnetic field now can act as a voltage to open the next round of voltage-gated channels. And we'll talk about how that gets done. So we'll lay out the ideas and the concepts of how action potentials propagate. And then what we'll do is move on to an idea of a generator potential. And we'll tell this story from the point of view of an imaginary neuron out at the tip of your finger. And these exist. Out at the tip of your finger, there will be a subset of sensory neurons that respond to touch and really respond to changes in the shape of the input region of that axon. Fundamentally, what we're going to do is we're going to deform the membrane. And when we deform the membrane, we're going to open a subset of channels called stretch-activated channels. Basically, what we're going to do is, see, by changing the shape of the membrane, we'll open these channels and ions will come in. Sodium will flow in. Well, this sounds pretty similar. We've talked about voltage-gated channels that when they open, sodium comes in. The same story will be true here as well to some degree. That is, when we open the stretch-activated channel, ions come in and depolarize the membrane. Now, one of the major differences here that you'll need to hold on to as we describe this is that the voltage-gated channels are self-perpetuating. What I mean by that is the influx of sodium recruits more channels, which then brings the membrane to threshold, and you have an all or none invariant action potential. That's not true for these. What we see here is the amplitude of the depolarization is proportional to the number of open channels. So the voltage-gated channel openings for an action potential are all or none. They're invariant. An action potential is an action potential. They all look alike. These are different. The more stretch-activated channels you open, the greater the amplitude. The longer they remain open, the longer the potential. So these potentials are said to be graded with the strength of the stimulus. The stronger the stimulus, the larger the depolarization. This is true for all manner of sensory input, but the one we're going to talk about are the ones that are turned on by changing the shape of the membrane. But again, we'll use this concept to harken back to our initial discussion of the lack of voltage-gated channels along a membrane. On our initial story here, there are no voltage-gated channels, so this potential will die out within a matter of a millimeter or two. So then we have to invoke a kind of interplay between those channels that have been opened by deforming the membrane and those channels opened by voltage. We're going to use the depolarization generated by the stretch-activated channels to signal the voltage-gated channels to open. So positive charge will come in here in the form of sodium. That positive charge will then be recognized by the voltage-gated sodium channels clustered in a region called the trigger zone. And if there's sufficient positive charge coming in through these stretch-activated channels that the membrane potential reaches threshold, we fire an action potential. And then that will begin the propagation of the action potential into the central nervous system, from the periphery into the central nervous system, because we'll tell the story from the point of view of the generator potential to action potential in a sensory afferent. So we'll try to tie all of that together. But let's begin with our thought experiment that we ran last time. And in this thought experiment, we can imagine that this is the conductal region. And let's take this panel and actually label it as action potential action potential propagation in a membrane mostly devoid of voltage-gated channels. That's a complicated way of describing what we had there yesterday. We said that all along this membrane, at intervals, there were these purple potassium leak channels. And then we said that we were going to aggregate right at this site our green voltage-gated sodium channels. So these are intended to be voltage-gated sodium channels. Now, for the sake of completeness, we need to put in a few of the counterparts of the voltage-gated potassium channels. Now, in this thought experiment, what I want to do is I want to put electrodes across the membrane at intervals along this imaginary axon. And here again are our leak channels. We need these. Now, what we're going to do is we're going to add some positive charge here in the form of sodium. Now, if it makes it a little easier for you to recognize this, imagine that this structure here is one of our pineapple neurons, where this is the input region. And a little later, we'll see that the input region is depolarized by opening neurotransmitter operated channels. Another name for these neurotransmitter operated channels are the ligand-gated channels. They're opened by binding a neurotransmitter. Those are separate and distinct, and we'll talk a lot about their physiology, but those are separate and distinct from these voltage-gated channels we find here. So you can think about the arrival of positive charge coming from the opening of these ligand-gated channels, or you can imagine we magically put in here some positive charge. Doesn't matter for our purposes here. All we need to recognize is that we're going to add positive charge here around in the neighborhood of the cytoplasmic side of these voltage-gated sodium channels. And from yesterday, you'll recognize that what this positive charge is going to do is it's going to move the S4 regions. By moving the S4 regions, it tugs on the gate opens, and now once the membrane potential goes from about minus 70 millivolts up to around minus 55 millivolts, that's a point of threshold. Once threshold is reached, all of the voltage-gated sodium channels in the neighborhood fire open simultaneously and depolarize the membrane to in the neighborhood of plus 40 millivolts. That's much of what we talked about yesterday. Then we said the potassium channels opens and repolarized the membrane. And this occurred because of the opening of the voltage-gated potassium channels occurring concomitantly with the closing of the voltage-gated sodium channels, their inactivation. That was much of what we talked about yesterday. What I want to think about now is what is the fate of the positive charge which has caused this depolarization to plus 40 millivolts in this kind of membrane. So imagine, because we have opened all these voltage-gated channels, now the inside of this membrane is positively charged, and it's a reflection of the idea that there's so much positive charge in here, we've gone from minus 70 to plus 40 millivolts. That's the depolarization. The question I left you with yesterday is, what's the fate of all this positive charge? What happens to it? Well, remember that there are potassium leak channels all along this membrane. And remember that the concentration of potassium in here is 110 millimolar potassium. And that the sodium concentration is 10 millimolar sodium. And one action potential barely affects its concentrations. What this means then is, because the extracellular potassium concentration all along this axon is in the neighborhood of about 4 to 5 millimolar, we have a great gradient for potassium, and the leak channels are open. So what can happen is potassium can leak out of these channels down the concentration gradient. So the way we're going to dissipate the positive charge, which has come across the membrane into the cytoplasm, the way we're going to dissipate that positive charge is to allow potassium ions to leave. Then if you take measurements at these intervals along the length of the axon, where all you have are the leak channels, then where the excursion initially was minus 70 to plus 40, down here a ways, it will go from minus 70 to maybe plus 10. And down here a ways, it may go from minus 70 to 0 millivolts. And here it may go from minus 70 to minus 10 millivolts. And here it may go from minus 70 to minus 50 millivolts. So by the time we get down to this point, the membrane potential goes from minus 70 to maybe minus 69 millivolts. So what I'm trying to illustrate here is simply that this extremely large potential, some 1/10 of a volt, the charge that generates a change in the membrane potential by over 1/10 of a volt, that charge will run out across the membrane through the leak channels. And because we're losing charge, the amplitudes of these potentials get smaller and smaller and smaller. And in fact, the numbers show, if you do this in a real cell, the numbers show that you can have one of these very large potentials, 110 millivolts, decay to less than a millivolt, in the neighborhood of about 2 to 3 millimeters. Well, think about that for a minute. Imagine you touch a hot stove with your hand. Now, you know if you touch a hot stove with your hand, you know what happens. You touch it immediately and you pull your hand back. But if all you had were an ability to initiate an action potential right at the trigger zone out here at the tip of your finger, and you only had the voltage-gated channels out the tip of your finger, the way I've described this, the change in potential across the membrane would go from the tip of your finger, maybe reaching your first knuckle. It would simply dissipate over such a short distance as to be useless. So what we need to do is we need to find a mechanism, a way of regenerating this potential. So we've generated the potential here, but we need to be able to regenerate it over and over again so we can propagate it along the membrane. So we're going to do that in 2 steps. So in the next panel, we're going to talk about propagating an action potential in membranes that contain many voltage-gated channels. Now, I should emphasize here, it's not just that there are lots of these channels, it's how they're arrayed. So we're going to take the same pattern. We're going to imagine that we have these two parallel lines that represent the plasma membrane or the axon. And this is the cytoplasm of the axon. And this, of course, is the plasma membrane. Now, in the above example, we clustered those voltage-gated channels at one site, but now what I want to do is change this pattern just a little bit. So that now along the length of this axon, we see this repeating pattern of the voltage-gated sodium channels. So these green guys are intended to be the voltage-gated sodium channels. Now, the green voltage-gated sodium channels will be accompanied by their counterparts of the voltage-gated potassium channels. And I won't draw all these in, but recognize that there will be the counterparts all along here of the voltage-gated potassium channels. These will be the delayed rectifiers that we talked about yesterday. The green channels are the green structures are meant to be the voltage-gated sodium channels. Now let's repeat the pattern we have in the upper board and simply draw in at intervals along the length of this thing our imaginary electrodes, which will now allow us to take measurements at intervals along the axon. I don't want to belabor it too much, but I'm trying to say here that all of these voltage-gated sodium channels are evenly distributed along the membrane. Let me, in fact, change this from many to evenly distributed. So now let's run through the same pattern. Let's imagine that we add positive charge. Sodium, some places coming in. We can imagine, just as we did above, that it's from ligand-gated channels. Regardless of how we do it, we increase the number of positive charges around the cytoplasmic side of those voltage-gated sodium channels. That pops the S4 region. When 3 of the 4 S4 regions pop, the probability the voltage-gated channel is going to open is pretty high. When those channels open, more sodium comes in. So all these channels now are emitting sodium. Now remember the sodium here. The sodium now has an electromagnetic field. The charge in the electromagnetic field now can affect this next channel, cause it to open, and sodium comes in. And sodium comes in here. And if we make recordings at each of these sites, so the initial site here, we see a recording where we go from -70 to +40, the voltage-gated potassium channel is open, and we repolarize the membrane. If we now measure it at this site, we see -70 to +40, and back down again. Wherever we measure along this membrane, we're going to see exactly the same potential. And the reason we see the same potential is that at each of these sites, we're opening the voltage-gated sodium channels, so we go from -70 to +40, and back down again. We can describe these potentials as action potentials are invariant. Once we have opened sufficient number of channels to reach threshold, once we have reached threshold and all of the neighboring sodium channels open, they always go to +40 millivolts, the equilibrium potential, more or less, of sodium. We open potassium channels and repolarize it. Now, we can propagate this potential along the membrane by using the sodium that comes in at one site to affect the neighboring sodium channel. Open that channel, open the next one. Open this channel, open the next one. So almost like a series of dominoes, we can sequentially open these voltage-gated sodium channels, and wherever we take a recording along the length of the axon, the potential goes from -70 to +40 and back down again. So we're generating and regenerating the actual potential at each of these sites. We do this, and as we do this, we, in a cascade, like dominoes, we open these actual potentials and we propagate. We propagate the actual potential. By sequentially opening voltage-gated sodium and potassium channels. So any questions to there? Yes?
All the voltage-gated sodium channels open up because of the sodium electromagnetic field.
So the question here is, are you telling me that all of these voltage-gated sodium channels are being opened by the electromagnetic field of the sodium which has entered the cell? Yes, absolutely. And each one of those will carry its maximum amount of sodium ions. And by carrying its maximum amount of sodium ions, if there are enough of these guys in the neighborhood, then that will generate the action potential. Now, if it helps, you can imagine how we could remove some of these. So let's say we have a gap in here where we don't have any voltage-gated sodium channels. Then, just as we saw above, the potential will leak out across the membrane. So if that gets to be so small that there's insufficient number of positive ions at this next channel to open it, then the action potential dies, because we simply don't have adequate positive charge to open the next set. And if we don't have enough, we can't reach threshold, we can't fire them. But as long as we have a continuous set of these voltage-gated sodium channels, we can open them like shoving over a domino and having them fall over sequentially. So you can think of it pretty much that way. Any other questions? Yes, in the back. So are you asking what's the difference between the upper one and the lower one? Yeah. So why is it? So the question here is, why is it this potential starts out big up at this site and then gets gradually smaller and smaller? And what's the difference between what I've shown in the upper panel and the lower panel? Well, if you notice in the upper panel, I've restricted the position of the voltage-gated channels just at the extreme left-hand end. So now those guys open, and then they inactivate. And they let positive charge in, sure enough. But now there are no other available sodium channels, no other available voltage-gated sodium channels to open to start the potential again. So in that case, because we can't start it again, then that positive charge leaks out across the membrane through the leak channels. So the potential gets progressively smaller and smaller and smaller. Whereas here, the potential doesn't get progressively smaller because we regenerate the actual potential at each of these points where we open additional voltage-gated sodium channels. So it's the distribution of the voltage-gated sodium channels which now permits the propagation of the actual potential. Yes? So the question, so fair enough. The question here for the first one is, why ever would you want to do that? And the answer to that is, in biology, probably not so much. You wouldn't do it, but I use it as an example of what's going to happen to the charge. And we will see, I can go back up to the upper panel. One of the important issues we'll run into next week probably, maybe tomorrow, is that out here in the input region, we lack these voltage-gated channels. We have only the ligand-gated channels. So when we open the ligand-gated channels and sodium comes in to depolarize the membrane, it depolarizes, sure enough. But the potential, the amplitude of that potential generated by opening these channels will get smaller and smaller. because it can't be regenerated by voltage-gated channels until we reach the trigger zone. And we'll talk a little bit about this in a moment when we talk about the sensory neurons. Let me go up here and then we'll come back. Yes?
So, is it happening, like, are the channels, the voltage-gated sodium channels opening and, like, that area is reaching positive 40, and then threshold is when the whole axon reaches negative 55?
Okay, so the question here is, what do we mean by reaching threshold? And do we have to reach threshold simultaneously along the full extent of the membrane? The answer is we can reach threshold in a local region. For instance, up here. We can reach threshold among these voltage-gated channels. And then once we reach threshold and sodium comes in, that will now lead to opening these. Now, you could take a measurement. You could do this in a neuron. You could take a measurement here and then take another measurement, say, 10 centimeters away. And what you would see is that when you take the measurement here, you immediately see the action potential. But it's going to take a while for these potentials to propagate along the membrane and reach the electrode down here. So round numbers, if you're let's make it easy. So that if the propagation rate in an unmyelinated axon is, say, a meter per second, and you put an electrode in here and you fire an action potential, you won't see the action potential drive the membrane to threshold down here a meter away until a second later. And so it's the gradual increase in positive charge, which is at infinitely small sections of the membrane, driving that membrane potential to threshold, and then the next infinitely small region. That's why calculus is very useful when you start calculating these things. And yes, and what you had a question first.
So how does the opening and closing of channels have anything to do with firing off a neurotransmitter?
Okay, so the question here, and I think I'll just defer this. The question is, how is it that these action potentials cause the release of neurotransmitter? Well, if we were to take this out here to the axon terminal, when the action potential arrives here and goes to plus 40 millivolts, it's carrying in positive charge. And what we're going to see is the positive charge at the site is going to open a voltage-gated calcium channel. And it's this influx of calcium across the membrane through these channels that's going to trigger the exocytotic vent. And we'll talk a lot about that. So but you're absolutely right. I mean, how do we go from these all or none signals of action potentials to the release of neurotransmitter to talk to the next cell? That signaling is carried out by the positive charge delivered by the action potential, but now that's not sufficient. That positive charge has to open voltage-gated calcium channels, let the calcium in, and then there's a cascade of events that the calcium initiates. Okay. There was another question, yes?
What would the full graph look like for axon? Like, if you're making little segments of it, what would the full graph look like for the whole thing traveling down the whole propagation?
Okay, so the question here is, what would the potential look like as it propagates along the axon? And it would depend on where you were along the axon. So if this is propagating in a meter per second, as we said a little earlier, then it's going to be a second later before we see that depolarization a meter away. Because the duration of these action potentials in here is no more than 1 to 2 milliseconds, then this action potential has long repolarized the membrane before the one a meter away has charged. Now, it's true there's going to be kind of a leading edge of depolarization, so that you'll have a leading edge of depolarization so that you bring the membrane to threshold, and you have to do that sequentially. But basically what we see is that these action potentials, let's see if I can answer it this way. You're asking the question, if we're propagating at, say, a meter per second, and these are a millisecond long, what region of the membrane would be depolarized and look all the same? Okay, so let's be careful of this. You're asking about the sum of these graphs. And these do not add together. They're all or none. They always go to plus 40. They're restricted by the equilibrium potential for sodium. So you can't add two of these together and go to plus 80. You can't get to there because you're limited by the equilibrium potential for sodium. So each one of them opens the sodium channels. The sodium comes in, but can't depolarize the membrane any more than the equilibrium potential for sodium. So we'll see here in a little bit that the small potentials that are produced by generator potentials, synaptic potentials, yes, they can add together up to about 0 millivolts. But these can't add together. So what you see is a regenerating potential at intervals along the membrane. Okay? Does that explain it? Not quite, perhaps. All right. Yes?
I think she means what would happen if you were to take all of those graphs and look at them as one graph cumulatively across the axon? Would it go like an average? It would be if you were to track the graphs as one series of those graphs laid over to the whole system.
Okay. I think we're working with a little bit of a misconception. And that is that this potential will be completed within, say, 2 milliseconds. But over 2 milliseconds, if it's propagating at a meter per second, it's going to cover 2 millimeters. So 2 millimeters of the membrane will be depolarized like this. But outside of that 2 millimeters, there won't be any depolarization at all. Although at the leading edge, you're right, you will get it slowly depolarizing a little bit to bring the membrane to threshold to open those voltage-gated sodium channels. So maybe the difficulty here is in envisioning this with respect to time. So what we see here is at T1. And this would be at T2 sometime later, and this would be sometime later. And if this were a meter, it would be, and we're propagating a meter per second, it would be a full second later before that potential would be recognized. Does that help? Okay, yes?
So with this bottom section, they're not drawn, and I don't think we've really mentioned it, but the potassium leak channels, are they still there?
So are the potassium leak channels still there? Yes, the potassium leak channels, I didn't put them in, but you need them in order to generate. You need them in order to have a membrane potential. Without them, you don't have a membrane potential. So they're there, but now any ion movement through these leak channels will be completely swamped by the movement, particularly through the voltage-gated potassium channels, because there's so many more of the voltage-gated potassium channels. And the permeability through those channels will be so much greater.
What were those black lines representing?
These are the electrodes. These are the electrodes taking the measurement. So so normally what I would do is I would show a thing here with a little arrow on it and to ground. That's the sort of universal symbol for measuring. That's a measuring electrode. It's measuring with respect to ground.
That's not in our neurons normally. That's just...
No. This is how we're measuring them. This is just how we would go in and take a measurement of these ion movements. Yes?
So which one is the accurate representation of actual neurons, or do we have both types?
So the question here is, which one of these represents an accurate description of a neuron? This is an accurate description of a neuron. That's not. That's a thought experiment. This one is what we would see in an unmyelinated axon because we haven't wrapped it with myelin. And this is what we're going to see in particularly a pain-sensitive neuron. Deep pain, the throbbing pain that you feel when you hit your finger with a hammer, that lasts for some time. That's these neurons. They're slow, but they're persistent. So anything else before we go on? Next thing I want to do here is I want to imagine this phospholipid bilayer. In fact, let me redraw it. So we'll take that single line and expand the single line out to our drawing of the phospholipid bilayer. And what I want to do on this panel is describe the concept of capacitance. So we'll take this panel and we'll label it as membrane capacitance. Capacitance really is nothing more than the ability to store charge. Across a non-conducting medium. Well, the non-conducting medium that we have in a biological membrane, of course, is the phospholipid bilayer. So if this is outside and this is inside, then remember the inside is at minus 70 millivolts with respect to the outside. So that means there is an excess of negative charge in here. But if there's an excess of negative charge here because we're minus 70 millivolts with respect to the outside, that means there's an excess of positive charge on the outside. This width of the membrane is only about 6 to 7 nanometers. Opposite charges attract. So the positive charge on the outside is attracted to the negative charge on the inside, and these charges are lined up right along the membrane, and they're being held there by the electromagnetic forces between the negative and positive charge across this exquisitely thin structure of the phospholipid bilayer. That's the idea of capacitance. Membrane capacitance, the ability to store charge across a non-conducting medium. This is a non-conducting medium, and we've stored charge across it. Now, the complication here arises when we have one of our channels. This is our voltage-gated channel. And we have described here how when we open the channel, sodium comes in. But now, one of the jobs of this sodium coming in is to discharge the capacitance of nearby membrane. So a great deal of the energy of the sodium which comes in at this site is effectively taken up by charging the capacitor, reverting from the negative charge on the inside to the positive charge. So the first thing the sodium does is offset that negative charge. That offset is required before we reach the next voltage-gated channel, because the capacitance must be discharged before opening neighboring channels. I should say voltage-gated channels. Now again, remember voltage gate is just a fancy term for charge sensitive. So if a lot of the charge coming through these channels is now taken up effectively by the sponge of the capacitance, we just don't have much charge left over to activate the next channel. That has implications for that membrane on the upper panel. It's saying we're just going to have a lot of ions coming through each of those channels to offset the capacitance to open the next channel. So it's a remarkably inefficient system. And it's this capacitance and the requirement of offsetting the capacitance that slows the conduction velocity down to around a meter per second. Got that? Okay, so how do we solve that problem? Well, let me solve the problem on the backboard. The way we solve the problem is to think about propagation of action potentials. In myelinated axons. So we draw the same pattern as above, two parallel lines. But remember when we were talking about Schwann cells and we were talking about oligodendrocytes, that at intervals the membrane is ensheathed, it's wrapped by concentric rings of the plasma membranes of the oligodendrocytes or Schwann cells. So this is the myelin sheath. And then at intervals, at intervals, there are these nodes of Ranvier, where we have naked membrane. So this is the node of Ranvier. The node of Ranvier is naked membrane, and what we do then is we restrict or cluster the voltage-gated channels at this site. So these are the voltage-gated sodium channels. Now, so the point I need to make here, and I'll give the numbers to it, then I'll try to explain it. I will try to explain it as a kind of concept. And that is capacitance. Capacitance in series. Capacitance in series adds as the inverse. The electrical engineers among you will recognize this immediately. It says that 1 over capacitance total, the total capacitance, is equal to 1 over C sub 1 over 1 plus 1 over C sub 2 plus 1 over C sub 3. We said that the plasma membrane, each of those plasma membranes is a capacitor. So now what we're doing is these consecutive rings of myelin, each one of those is a capacitor. So what we're doing is that the total capacitance across this region, this is a terrible capacitor. Quantitatively, you can recognize it by 1 over C total is equal to 1 over C1 plus and so forth, where you'll have thousands of these. But conceptually, you can simply recognize that in the upper panel, we see how close those charges are across the phospholipid bilayer. But now, when we have hundreds or thousands of these phospholipid bilayers, we now have a great distance between the positive charge on the outside and the negative charges on the inside. They just don't have, they're too far away to have much electromagnetic field effect upon one another. Okay? So now, sodium comes in. It has an electromagnetic field. There's hardly any capacitance in this internodal region. So that means the effects of the sodium are free to propagate almost instantaneously through the axoplasm. So almost immediately after the sodium comes in at this site, that electromagnetic field is recognized at the next site. That opens these voltage-gated channels. So sodium comes in, and because there's little capacitance here, you're free not to absorb a lot of that sodium and positive charge by the negative charge, and we move to the next node. When we do this, now the action potential propagates at the neighborhood of about 110 meters per second. Let's leave it there, and we'll come back to